Thank you so much for having me, everyone. I'm Jonah Casebeer, and I'm a PhD candidate in the CS department at the University of Illinois. And I'd like to thank Julius, the DSP seminar, and Karma for having me today. I'm going to talk to you a little bit about some of my work in meta-learning for adaptive filters, which we call Meta-AF. And the brunt of this work has been with my advisor, Paris, our key collaborator, Nick, and some other people that I'll mention along the way for subsets of the problems. I'll start off in this talk by providing a really brief introduction to adaptive filters. So what they're useful for, some little insights into how they work, and how to design them. And then I'll segue into meta-adaptive filters, or our actual contribution. I'll talk about the development of meta-adaptive filters and some insights into trade-offs for developing them. And then finally, we'll conclude with a suite of case studies and ablations where we actually benchmark meta-adaptive filtering tools on a suite of canonical adaptive filtering problems. For each of these, we'll examine different scenarios and try and pick out both pain points and success points. Adaptive filters themselves are in basically every single multimedia device that you own. They're the tools that power things like echo cancellation algorithms, equalization tools for things like active noise control, dereverberation tools, so things that help smart assistants pick up your speech, and directional listening or beamforming tools, think speech enhancement and source separation. These algorithms, while ubiquitous, are very hard to design. At their core, adaptive filters are processing or little online processors that take an audio snippet, process it in some way, so any of those tasks I mentioned earlier, and then spit out a processed audio chunk. The particular configuration for the parameters that drive this processing or filtering procedure are controlled by an optimization algorithm or an update rule. And typically, this update rule is developed ahead of time offline by some expert that has domain knowledge about the particular adaptive filter task, maybe the device it's running on, or the kinds of environments it'll be deployed in. To be more concrete, in this talk, I'm going to represent our adaptive filters by H, and they're going to be parameterized by some parameters theta, indexed by the time index, since all this processing is streaming. Depending on the application, they'll have different sets of input parameters. Our update rule, or the ones that are human-derived, are going to be additive, where on the left, theta tau, we have our current parameters, and on the right, we have some derived update, delta of tau. To be concrete, we can walk through a simple adaptive filter problem. I'll describe how we optimize it and unroll it, and this will let us connect to how we're actually going to learn these procedures. So the simplest and arguably most canonical adaptive filtering problem is system identification. System identification is basically just streaming linear regression, where you have access to only one column of your data matrix at a time. So our filter, H theta, is going to get some input U, and its forward pass, or its operating procedure, is just going to be applying its FIR weights or its weight matrix to that input, where the only constituent parameters of theta are those FIR parameters W. We're going to call that output Y. And now that we've defined our simple filter forward pass, we actually need to train it. So we're going to need to develop a loss function and then an update rule. In the toy case, we're just going to select mean squared error as our loss function. And this lets us develop a straightforward update rule, something like stochastic gradient descent, where I'll hand select some step size and multiply that by the gradient. Unrolling this setup, or how you would actually run this algorithm, is you get some input at time 0, you apply your filter, you get an output. You then compute the loss, use that to update your filter, and get another output. And then you keep running this iterative procedure until either you've finished processing all the audio in the scene, or you've reached some sort of convergence criterion. reaching those convergence criterions or actually processing all the audio in the scene is pretty hard. So if you want optimization rules that will be robust to the kind of anomalies that users will create or actually work really effectively, it's going to take a lot of expertise to do this. And we're going to try and trade some of that expertise and augment our signal processing engineers here with some learning mechanisms. So instead of hand developing these optimization rules that are going to control our filters, we're going to try and learn them offline ahead of time using some data set of signals and leveraging compute. So the core proposal of this Meta-AF work is to try and automate the tuning and design of your filtering algorithms. And the idea is that we can both save development time, so reduce how long it takes to get your adaptive filter to work well. And then I'll hopefully convince you that in some cases, we can actually beat expert tuned filters. The main contribution for doing this is going to be a generic formulation, or what we're calling a universal formulation, that will work for all kinds of differentiable streaming processors. The kinds of tooling we're going to use to get this to work are really related to other inference time optimization tasks that you might be familiar with today. So think things like style transfer or the popular 3D renderers. Our proposal is centered on making this conceptual decomposition of your adaptive filter into two parts. The first of those is the model. So this is the processor that actually performs your echo cancellation, noise suppression. And the other is your optimization rule. That's the stochastic gradient descent, recursive least squares, Kalman filter, or whatever your favorite optimization rule is. The insight is that selecting your model is an easier task in that it doesn't take as much work to identify, oh, this would sound better if there was less echo, or I'd like it if the noise are removed from this. But getting an optimization rule to do that well is actually really hard. And we're going to try and learn that optimization rule without any manual intervention. So the idea is that someone will tell us what model they want, and then we will automatically learn an optimization procedure without any interference or assistance required. And we're doing that by framing it as a meta-learning problem. The intuition here is that when you are learning the parameters of your model, so running optimization, it's a learning task. We're trying to learn an optimizer, so it's a learning to learn or meta-learning setup. We can start with what we actually want our optimization algorithms to do, and then from there we can walk backwards and reason about how we're going to train them. So we'd like both our adaptive and meta-adaptive filters to predict additive update rules. So on the left, we've got an update rule, which is developed by some expert. We estimate some update delta of tau. That update will have been based off of our knowledge of the filtering algorithm and some particular loss function that accompanies the filter. This is usually motivated by physics, and it's baked into the filter. We'll manually develop that optimization algorithm if you're doing classic adaptive filtering. In the meta-adaptive case, we want to learn how to predict this update rule. So our update is going to be driven by some neural network G, parameterized by phi. And we're going to try and train this neural network without extra inputs or knowledge about the adaptive filtering scenario. So we're going to train it using a proxy or meta loss, LM, where that LM is something that we automatically derive for you given your adaptive filter loss and your adaptive filter setup. We'll train across this whole thing using standard deep learning techniques, so batched SGD, in particular Atom. We can take that meta-adaptive objective and actually reason about why this objective is easier, why it simplifies things. So walking from the inside out, we can take that innermost term, the model, so the loss on our particular filter. And what makes these easier actually boils down to a question about specificity. So that model, or H, is task and scene specific. So being concrete here, let's say H is an echo canceller. An echo canceller can only perform echo cancellation, that's task specificity. And an echo canceller with parameters theta only performs echo cancellation effectively when theta are the correct parameters for the scene. That's scene specificity. Your optimization algorithm, its job is to find those thetas. So it's not scene specific, but it is task specific. and that if you want a really high performing optimization rule for echo cancellation, you need to develop it for that task. The insight in this work is that this outermost section, or the meta training procedure, is actually universal. It's not dependent on your particular adaptive filtering task or the scene you want to deploy it in. That means it doesn't take specific insights about those tasks or scenes to train it. Instead, you have to trade it for data. And we have a series of works where we describe how to do this and some trade-offs that I'll try and talk about here and provide some motivations for. One component of this that we found is pretty critical is how you actually configure that optimization rule. So that G5, what your neural network architecture actually looks like. We're going to set up our neural network to solve or optimize all the parameters you're processing simultaneously. So your processing has some number of parameters that need to be tuned all at once, and we're going to tune them all at the same time. Just like when you're training a neural network, say, you train all weights in all layers simultaneously, or like when you're fitting a filter, you update all taps at the same time. We're going to run one instance of our optimization algorithm or rule on each of those parameters. And in series, we're going to extract some task agnostic features. So these are features that work for any of the adaptive filtering scenarios that we'll talk about. We'll share information across these simultaneous optimization problems, and I'll get into how you actually do that a bit more later. And then we'll maintain some sort of per optimization problem or per parameter dynamics. So that is, we'll have a recursive module that has some state, and it'll have a state that is unique for each of these parameters. Intuitively, if you think of something like atom, you have a separate momentum term for every parameter. You might notice this looks a lot like the learning to learn setup by gradient descent, and it's very motivated by it. So we make a variety of domain-specific insights, so things about how you actually extract the features, the actual configuration of this module, and training tricks that over a learning to learn setup actually get us multiple decibel improvements in most tasks while reducing complexity by 1 to 2 orders of magnitude in terms of flops. Yeah, of course, go ahead.
How do you derive the initial parameters that you're optimizing for an adaptive filtering task? Like the optimal parameters that you're initially training your algorithm around?
Yeah, that's a great question. So this is an excellent question, because my next slide is how do we actually train these, right? Because we've developed the architecture we actually want to run. We've identified some tasks. How do we actually train our modules to solve these tasks? So taking that system identification example again, where we've got that same linear regression filter, and now instead of our SGD update rule, we've got our neural network. We can start with that unrolled algorithm that I displayed earlier. So in this algorithm, the part that we're trying to replace is that gradient processing. So we actually compute the update. We're going to swap that out for our neural network module. And we have 2 different ways that we can try and train this module. Both of these we're going to require running basically an optimization forward pass. So you have to run your optimizer once, and then you'll estimate losses in one of 2 different ways, which we'll contrast. The first of those is the independent loss, or the independent training scheme. This takes each of those instantaneous losses and then sums them up in an order invariant fashion. We call this independent because it doesn't model the temporal sequence of those losses. The second way that we'll propose to train them is using an accumulated loss. So we'll aggregate all the outputs of your adaptive filter across time and then compute that same loss on those. Both these losses get to use the same information, but they make slightly different assumptions about boundaries between frames and how things actually get averaged. For both of those, we'll just use backprop through time to train our optimizer. So if you're familiar with training RNN modules, it's just like that. And the length that we unroll our optimization procedure for, or how many steps we train on, is just your truncation length in backprop through time. So that's L in this setup. We're going to evaluate ourselves on a whole suite of adaptive filtering problems, where for each of them, we're going to use one same meta training procedure to give us a custom optimizer for each of those tasks. The first task, and the task we're actually going to ablate the configuration of this meta-adaptive filter on, is system identification. System ID, or linear regression, in this case, is the task of recovering the transfer function between a microphone and a speaker in an online fashion. In particular, we're going to pretend that there's some unknown system, which is a LTI system, and we're going to fit a frequency domain adaptive filter to match its outputs to the outputs of the unknown system. I'm displaying performance here on the y-axis in signal to noise ratio between the two outputs. So higher is better here. And on the x-axis, I'm displaying a whole suite of algorithms. Let's focus on the ones to the right of the dashed gray bar for now. These are different ablations of our meta training procedure. And there are two key ones here that I'll pick out. The first of those, and what we find is most critical when training your meta-adaptive filters, is how you actually build your meta loss. So what you actually use to train it. The most important of these is using log pre-processing. So you want to reduce the dynamic range of the gradients that you compute of your optimizer. So optimize their log, not the task objective directly. The second most critical is using the accumulated loss instead of the independent loss. So modeling the boundaries between frames is important. And finally, the least critical is the truncation length for the unroll. It doesn't really matter what you pick as long as it's bigger than 1. For our task, we'll pick 16 since it's a reasonable trade-off between between train time complexity and how well it works. Your unroll value and the accumulation and the log, none of these have any effects at test time. These are all just training procedures. An effect that does have an impact at test time and that we find is important is how you perform your feature extraction. So we have some task agnostic features that we extract, or adaptive filtering generics, the input, output, error, and target for the filtering problem, all of which we provide to our optimization algorithm. Providing those improves performance a lot. On the left of the gray dash bar, I've got a suite of baselines, which we'll become very good friends with over the next couple experiments. These are a least mean squared algorithm, RMS prop, normalized LMS, and a diagonal recursive least squares setup. These are all running in the frequency domain, and I've grid search tuned them on a held out validation data set. So on this synthetic task, we can see that our best performing setup of our meta-adaptive filter is actually matching the performance of our diagonalized recursive least squares algorithm. So this is good news and hopefully encourages us to go tackle some harder tasks. Before we get to those, though, we want to evaluate what kind of optimization rules we're actually learning and whether we're learning some sort of optimization primitive or something that only solves a specific optimization task. So in this task, each group represents an adaptive filter order. So that's how many taps that frequency domain adaptive filter has. And the bars within groups represents the order of the underlying synthetic system. So for some intuition before we get into the results, this is the results for when you try and fit a 256 tap filter to, on the leftmost bar, a system which has 256 taps. That works well because the lengths are matched. One to the right is 512, doesn't work well, it's too long. We can jump to the next bar and see our intuitions hold again. So a 512 length system can represent a 512 length underlying system and a 256 length one, and so on. The good news about this plot is we produce this using a meta ID algorithm or a meta adaptive filter trained for system ID only on 1024 tap filters with underlying systems of length 1024. And then the rest of this plot is all actually produced at test time. So the model has never optimized filters that are this long or this short, and it's never encountered systems that are that long or that short. So it's an exciting kind of generalization. Now that we've hopefully convinced ourselves that we can perform reasonably on synthetic tasks and we've developed our training procedure, we're going to apply it to one of each of the canonical adaptive filtering problems. So these are system ID, inverse modeling, prediction, and interference cancellation. The first of those that we'll actually go after is acoustic echo cancellation. So AEC is the task of own playback reduction. It happens anytime you have a device that's both emitting a signal and recording it at the same time, and it doesn't want to record its own signal. We set this up as, again, trying to find the parameters of some unknown system where this is made more challenging by confounding signals, and that your device is not the only thing emitting signals in this scenario. So there are going to be confounding signals that also get recorded. If you want to think of this like a linear regression problem, it's like the labels being noisy, except the labels will be noisy in a correlated fashion, which makes it especially hard. Here, instead of fitting a simple frequency domain adaptive filter, we're going to fit a multi-frame or a multi-delay frame frequency domain adaptive filter. And we're going to listen to the echo reduced output of these. So that's the value we'll use when we compute things like perceptual values. In this setup, for that perceptually motivated descriptor, we're going to use STOI, or short time objective intelligibility, bounded between 0 and 1, where higher is better. Here I'm showing it plotted between about 0.75 and 1. And we're comparing Meta-AEC, shown in light blue on the top, to an industry-grade echo canceller, and then a suite of academic implementations. So a diagonalized Kalman filter, block diagonal recursive least squares, normalized LMS, RMS prop, and LMS. Even though we don't explicitly train for STOI, again, we just use that automatically derived meta loss, Meta-AEC actually sounds better than these baseline optimization rules. It doesn't just sound better, it actually has more favorable optimization dynamics. So in the right plot, I'm displaying ERLE, or a metric of how much echo is removed, where higher is better. And we see that Meta-AEC, shown in light blue with the X's, both converges to a higher ERLE value faster, and then across that orange shaded region, which represents a change in the unknown system, actually recovers faster. So it's converging and reconverging faster. So it finds the right parameters quicker and resets its internal state to find new parameters faster as well. This particular configuration of Meta-AEC is actually, to the best of our knowledge, the best performing linear filter on the Microsoft AEC challenge, where we've compared our performance to a couple other linear filtering algorithms that are on the leaderboard there. This setup is real-time capable on a single CPU core, and the optimization algorithm itself is pretty small. It takes less than 50 kilobytes to store. But we can do better. So those rules that we talked about there were diagonalized rules, right? We were optimizing each parameter of our adaptive filter separately, or treating them as separate tasks. Intuitively, we know that's not true. Frequency K and K+1 or K-1 are related in some way. But building algorithms that can leverage higher order frequency relationships is pretty challenging. We know they matter, though, because things like independent vector analysis, or IVA, have benefited from them greatly. But it took a lot of mathematical insight to move from something like independent component analysis to independent vector analysis. In this framework, instead of needing that kind of insight, though, you just need to provide the structure to learn those modules. So the point here is that learning to model higher order frequency relationships can just be instilled in your network by using the right neural network architecture. Concretely, in Meta-AF, we have some optimization rule that makes an implicit diagonal assumption. So we tune each of the frequencies of our frequency domain adaptive filters separately. In higher order Meta-AF, we're going to introduce a upsampler and downsampler, or modules that learn to do higher order modeling. In this setup, I'll talk about using these to make both block and banded relationship assumptions, but you can make whatever kind of relationship assumptions you want based off of your configuration of U and S. In these plots, on the left, I'm displaying ERLE again. On the right, I'm displaying flops. So left is a measure of performance, right is a measure of complexity. The three gray stars I've got here are different sizes of our diagonal update rule. So this is increasing or decreasing the size of the neural network. For the diagonal update rule, we find that increasing and decreasing its size doesn't change performance much, but it does change complexity, right? Which makes sense. We make the neural network bigger, it takes more flops to run it. So that's a more expensive neural network, but it's performing the same as these smaller ones. Going for higher order update rules lets you access a whole suite of different trade-offs along this curve. So the top grouping here represents banded modeling, and the bottom grouping represents block modeling, where the x-axis here represents how many frequencies you model jointly. It also lets you unlock different kinds of complexity trade-offs. So neural networks effectively let you cheat, since the inner dimension or the hidden state size is not dependent on the input or output size. So you get to amortize in ways that you can't with classic optimization rules. To pick out some examples here, on the left plot, this module right here, so the 32 hidden unit diagonal optimizer, uses the same amount of compute as our banded optimizer, yet the banded optimizer performs a couple decibels better. We can also go to the other plot and make the reverse inference. So our 32 hidden unit diagonal optimizer performs just as well as a block optimizer with a group size of 5. So we can get multi-decibel performance improvements, or we can reduce complexity by a decent amount of flops. And these kind of performance improvements actually translate to downstream effects that matter. So here we're taking that same echo cancellation challenge, which has noise in it, and we're training a speech enhancement module, so specifically a magnitude masking speech enhancer on the outputs of these linear filters. So we've custom trained a speech enhancer for each one of these. We find that using these higher order rules improves STOI performance both right after the AEC, so the linear filter works better, but this improved performance actually translates to better downstream performance. So the outputs of the neural network speech enhancer also sound better. This is good news because we spent a lot of effort trying to make our optimization rules better. So we would hope they translate to performance improvements that you can't just get with the straightforward speech enhancement setup. In short, going for higher order rules is better, faster, cheaper, and I think the right way to do Meta-AECs. I would like to really acknowledge undergraduate ECE student Junkai Wu, who is a core contributor on a lot of this work and actually ran all the experiments in this particular plot. The next task we'll evaluate is inverse modeling, or equalization. In the equalization setup, you're basically solving a system identification problem, but instead of recovering the forward system, you're trying to recover the inverse system. So we're fitting that same frequency domain adaptive filter to some unknown system, and we're going to evaluate those outputs. Here, I've plotted a particular recovered system, so the magnitude response of an inverse system on from the test set. The black line represents the true system, and the blue and red lines represent our optimization rules, or what they've recovered. The blue one is Meta-AEC, and the red one is our grid search tuned RLS. It's hard to see them because they overlap, but I also display two variants of those algorithms where I've played with turning optimization constraints on and off for the equalization setup. Zooming in a bit more, we find that our Meta-AEC algorithm is actually performing a better job at recovering the hard parts of this filter, so those peaks or notches. And this also translates to better optimization behavior, where our Meta-AEC algorithms typically converge faster than their recursive least squares baselines and recover higher fidelity solutions. What we've ablated here is a constraint on the adaptive filter. So because you're learning your optimization rule, if you have some filtering dynamics that are unique to your task, your optimizer can learn to be aware of them. So the particular constraint I've toggled here is we're using overlap save. And in overlap save, you can either use a aliased or an anti-aliased filter. And I've toggled that aliasing. And we find that the performance drop is actually smaller for Meta-AEC, meaning it's learning something about that constraint when you're training it. Moving on to a little bit harder of a task, we'll tackle prediction. And here, the particular prediction task we'll go after is dereverberation, or a common pre-processing step for things like speech-to-text systems. We're using the weighted prediction error formulation. So the intuition here, or the hypothesis, is that given a delayed set of frames of reverberant speech and some future frame, the only part of that frame that's predictable from the delayed frames is the reverb. So intuitively, that means that the residual from your prediction is hopefully your dereverberated or anechoic speech. Implicit system here is that delay, and we're going to experiment with this both for multi-frame and multi-channel adaptive filters. So we'll run both 1, 4, and 8 microphone variants of these adaptive filters. We're going to evaluate how good that dereverberated output sounds. The first metric we're going to use for evaluation is signal to reverberation ratio. So this is basically how big was the residual. Smaller is better. And we're comparing to NARA, a block diagonal recursive least squares algorithm with some specific insights about how to build normalization factors based off of speech statistics. We find that Meta-WPE for both the 1, 4, and 8 microphone variants converges faster and has lower values when converged. But this is an interesting failure mode of the Meta-AF system. It actually sounds much worse. So the intuition here is that while the optimization task is prediction, and we're solving the optimization task really well, as you can see via SRR objective, prediction isn't a perceptually pleasing task. So our optimization objective doesn't correspond with how we actually want things to sound. This is actually a known phenomena for the online WPE scenario, and there are a couple works that try and address this based off of regularization schemes. And I think incorporating something like that here would probably fix this issue. But in short, Meta-AF won't solve everything. If your optimization objective is wrong, then so will your optimizer. To verify that that mishap wasn't because of the multi-channel setup, we'll conclude with a beamforming task. So here we're going to use the generalized side lobe canceller beamformer, or GSC, where we're going to assume that some other system has told us the look direction or the direction that the target speech is coming from. Our frequency domain adaptive filter will run on the output of that, and we're going to train a multi-channel frequency domain adaptive filter. So it's going to use 6 microphones. We're going to listen to the quality of that output speech for 2 different scenarios. One where we go after speech enhancement, so one speech source and then some diffuse noise sources that we try and suppress. And the second will be a source separation task, where we have 2 simultaneous speech sources and we want to extract one of them. For these 2 setups, I'm going to use STOI improvement, so the metric we had before, and SISDR, or scale invariant signal to distortion ratio. Intuitively, SDR captures something about how much interference suppression you're performing and how many artifacts you're introducing. For both these metrics, higher is better. We grid search tune those baseline algorithms again on a held out validation data set. And for the SISDR case, we find that both for speech enhancement and source separation, so diffuse and directional interferes, Meta-GSC is providing more suppression with less artifacts. We actually verify this further by breaking out the BSS eval metrics in our paper, but for space, I've just plotted SISDR here. So it's doing a better job at the signal level task, and it also sounds better. We're scoring better perceptually on the STOI metric. Since this is just an optimization rule that's driving the configuration of your beamformer, you can also plot the response plots from those beamformers. So here I have a spatial response plot at about 1 second into a file at about 1 kilohertz. The way you read these is that the radius represents suppression in dB, so 0 dB is no suppression. And the further in a line is, the more suppression it's applying at that angle of arrival. Since these algorithms are using the GSC setup, they're not suppressing at all towards the look direction, which is what's supposed to happen. And then we see that Meta-GSC in blue is actually steering sharper nulls, or it's suppressing more in the directions of the noise. So this is good because this matches our intuitions for how beamformers should work. And it's good to see that our neural network optimization rules are actually kind of abiding by this. We've blitzed across a whole bunch of adaptive filtering scenarios, and we have some others that we study in our paper as well. We also evaluate echo cancellation without a echo path change to look at peak convergence performance. We evaluate equalization using a couple other metrics and in mean, not just looking at convergence plots. We have more directional listening setups where we look at other evaluation metrics, so signal to artifact, interference, and distortion ratios. We have the Dereverberation setup that we talked about and our system ID ablations. Across all of these tasks, when you measure your performance with respect to your optimization objective, Meta-AF beats all the expert and hand-tuned systems we've been able to compare to. If you measure your performance using a perceptual objective, there's the WPE mishap. In short, with Meta-AF, you're able to learn custom adaptive filters for any particular task. The training procedure for those adaptive filters is unsupervised or self-supervised, and that we recycle the loss that comes with the adaptive filter. So if you have the data to run your adaptive filter, you have the data to train your optimization rule. And this actually works in practice. We've actually tried training optimization rules on real echo recordings and found that they perform better than our baselines in those setups too. Across all the tasks that I talked about, we performed no manual intervention. So we built our one meta rule, and then we applied it identically to each subsequent problem. So no changes. In short, no custom data, no manual work to do this, and we still got high quality real-time capable systems. So beyond the echo cancellation setup, all subsequent tasks also have real-time factors of less than 0.5. So they're real-time capable on a single CPU core. And I'm sure that could be improved with better code. I don't think the story ends here, though. There's loads of future work that could be done for meta-adaptive filtering algorithms. Beyond the building better optimizer architectures that I touched on, which I'm sure could be pushed further. You could also go after better training procedures. So we've talked about self-supervised adaptive filters. You can make supervised ones. You could try and fine tune on real data. You could figure out ways to leverage different data sources. I think there's lots of work that you could do. And you could go after more complex systems. So in real telephony or music processing pipelines, it's not just one filter in isolation. There's a whole stream of them that need to be controlled. And I think this is where the real complexity comes into play. And I imagine with Meta-AF type systems, you could learn how to simultaneously control or optimize whole banks or suites of processing tasks. In summary, across this, I hope I've convinced you a little bit that meta design can actually be a little bit simpler. And we trade some simplicity for needing extra compute and data offline, but not online when we're actually running the task. The rules you learn with these algorithms, when set up correctly, are pretty fast, they're relatively robust, and they're relatively general in that they're adaptive to different sizes of adaptive filters. I've got some 300 audio files up on my website if you want to give them a listen. They're non-cherry picked. They're just the first 5 samples from every data set. And I've also got a code toolbox that implements all the procedures I've talked about. So I've released the core training utilities for training Meta-AFs, as well as each of these specific implementations. And if you wanted to make your own implementation, all you have to do is write your filtering forward pass and its loss. And then my wrapper manages the rest of the complexity behind the scenes. I, of course, have got to thank a couple people for doing this work with me, in particular my advisor, Paris, collaborator, Nick, Junkai, and also our funding sources, so USDA, NIFA, and of course, Adobe. Yeah, happy to take any questions.